Hello students, this is Professor Chalai, and in this video we're going to look at diffusion and effusion of gases. As always, you can follow along with our Chapter 9 workbook. By the end of this video, you should be able to define diffusion and diffusion, and also to use Graham's law to compute various properties of gases. Let's get started. So, before we get onto effusion and diffusion, let's talk about briefly what the mean free path is, because I touched on this in a previous video, but I just want to give it a formal definition. So in one of our earlier videos, we talked about how we can think of the pressure that a gas exerts on a container as coming from the force of the gas molecules hitting the walls of that container, right? So gas molecules are randomly moving, bouncing around, and so the pressure is the force that it exerts on the wall. I did mention that if we were to reduce the volume of the container, right, but we keep the number of gas molecules the same, so let me draw 6 gas molecules in here, then the distance that the gas molecule has to travel before it hits into something else is shorter, right? Like compare that to the distance this gas molecule might have to travel to hit the walls of the container. It's longer. That average distance that the gas molecule has to travel before hitting something is what the mean free path is. We said in this case the pressure is higher because the distance the gas molecule has to travel before it hits the container is shorter, even though the number of gas molecules is the same. So that's the definition of the mean free path. It is the average distance a molecule travels between collisions. And we're going to look at this a little bit more detail in a few later videos. But now let's move on to diffusion and effusion of gases. They sound very similar, but and they are in fact similar processes, but they're slightly different. They both deal with the spreading or moving of gas molecules, but in the case of diffusion, right, this is the dispersing of molecules from a concentrated area to be more evenly concentrated. So for a definition, let's just write diffusion is the process by which molecules disperse, molecule starts with an M, in space, responding to changes in concentration. My handwriting there looks horrible. All right, so let's look at, let me draw a box. And let's say that, I don't know, there's some kind of gas in here already, green gases. But let's say we did some experiment or something and we somehow release a bunch of gas molecules in this area of the room, right? We know that the gas won't stay in that area. In fact, after some time, could be a short time, could be a long time, what happens is, the green molecules are still everywhere in the room, but that purple gas would now be diffused throughout the whole room, such that the concentration of the purple gas is the same throughout. That's what diffusion is. You have a situation where there's a higher concentration of the purple gas here, but no low concentration of the purple gas out here. Eventually, after a long period of time, that purple gas will diffuse and be more evenly concentrated throughout the room. In Chem 160, we'll learn exactly why that happens. Okay, effusion is a similar process, right? It's the movement of gas molecules, but in this case, it's the movement of gas molecules through a tiny opening. So in the case of diffusion, it's just a big room where you have different concentrations of gases. In effusion, right, we have a tiny opening that gas molecules can pass through. So in effusion, right, it's the escape of gas molecules through a tiny hole. So think about gas escaping from your tire, for example, or a balloon that's popped. Well, technically when a balloon is popped, the hole gets big pretty quickly. So yeah, think about holes in your car tires or bicycle tires. So that's effusion and diffusion. Now, you might think, okay, let's think of effusion, right? We have a little hole. This is a wall, this is a wall, and this is a hole that some gas molecules can try to escape, right? The rate at which that gas tries to escape that tiny hole depends on the size of the gas molecules, or more specifically, the molar mass of the gas molecules. And so you might imagine that the larger or the heavier the gas, the slower it will try to escape, or it will be able to escape through this tiny hole. And so Graham's law simply gives us an expression for the rate at which effusion happens. It's proportional to 1 divided by the square root of the molar mass. So rate, remember, measures how fast something happens. So rate of effusion is usually measured in amount of gas over time. Amount could be liters of gas, moles of gas, any of that stuff. But most rate measurements are per some unit of time, usually per second or minute or hour, depending on how long the gas, well, whatever relevant unit we're looking at. So the rate of effusion for any gas is proportional to 1 divided by the molar mass of that gas, square root of the molar mass. So we don't know what this constant of proportionality is. Remember that proportional sign means that the rate is equal to some constant, let's call it C, times this factor here, 1 divided by square root of the molar mass. Now, we don't know what this constant C is, and this constant C will be dependent on lots of different things, and we're not really interested in finding it. However, if you have two different gases, let's say we have this red gas and another purple gas, right? So the C here would be the same under the two different conditions. So if I divide these two equations by each other, the C's will cancel, and what we end up with is the rate of the red gas divided by the rate of the purple gas is equal to the square root of the molar mass of the purple gas divided by the square root of the rate of the red gas. And that's what this equation on the left over here is telling us. The rate of effusion of some gas, let's call it A, is equal to, divided by the rate of effusion of some gas B, is equal to the square root of the molar mass of gas B. So let me use those colors again: red, red, purple, purple, right? The rate of effusion of B is rate of effusion of A divided by the rate of effusion of B is equal to the square root of the molar mass of B divided by the square root of the molar mass of A. So those two things are on opposite sides of the division line. So using Graham's law, we can figure out how fast gases are going to diffuse, or rather effuse, through small openings, right? So let's look at some practice problems involving rates of effusion. Let's look at number 37. It asks us to calculate the ratio of the rate of effusion of hydrogen to the rate of effusion of oxygen. So hydrogen to oxygen, let's do that. So the rate of hydrogen, rate of effusion of hydrogen to the rate of effusion of oxygen, right? Those are the formulas. Is going to be the square root of the molar mass of oxygen. It's O2, so the molar mass is 32.00 grams per mole. The rate of effusion of hydrogen, the molar mass of hydrogen is 1.01 times 2, so it's 2.02 grams per mole. If I plug all of this into my calculator, I get a number like 3.98. So this means that the rate of hydrogen to the rate of oxygen is 3.98 to 1, right? Which makes sense. Hydrogen would effuse through the tiny opening 3.98, almost 4 times faster than oxygen, because hydrogen is a much tinier gas with a much smaller molar mass. So whenever you do these rates, make sure the numbers that you get make sense, right? Hydrogen should be much faster than oxygen, so the rate for hydrogen is much larger than the rate for oxygen. Okay. With that, try numbers 38, 9, 40, 41, and 42 on your own, and let's see where how far you can get. They all involved using this equation, sometimes in clever ways to find certain properties of the gas. And when you're done, you can unpause the video and I'll go over each of them with you. Okay, let's look at 39. At a certain temperature and pressure, right? Those are all the things that determine the constant C, which we're not going to deal with right now. At a certain pressure and temperature, nitrogen infuses at the rate of 79 milliliters per second. So let's write that. The rate for nitrogen is 79 milliliters per second. So remember up here I said the rate is measured usually in some amount of gas divided by some unit of time. Here the amount is measured in milliliters, the time is measured in seconds. Okay, so under the same conditions, what rate will sulfur dioxide diffuse? So we want to find the rate for sulfur dioxide, right? So let's set the equation up. So we know that the rate of nitrogen divided by the rate for sulfur dioxide will be equal to the square root of the molar mass of sulfur dioxide, which let's do it the other way around, actually. Let's put sulfur dioxide on top. The rate of sulfur dioxide, because this is what we want to find, it's easier to put the thing we want to find in the numerator rather than denominator, over the rate of nitrogen. So it'll be square root the molar mass of nitrogen, which is 28.02, divided by the molar mass of sulfur dioxide, which is 64.07, and that gives us a number of 0.6613. So that's the rate of SO2 over the rate of N2. We know the rate of N2, right? We're given it right up here. So this means that, let me write that again. The rate of SO2 divided by the rate of N2, which we just said we were given what that is. It's 79 milliliters per second divided by 79 milliliters per second. All of that is equal to this number that we just calculated, 0.6613. So if we want to find the rate of SO2, we just take 0.6613, multiply it by this number, 79 milliliters per second, and I plug this into my calculator and I get a number like 52 milliliters per second as a rate of sulfur dioxide. Does this make sense? Well, sulfur dioxide is a heavier gas than N2, so the rate for sulfur dioxide should be lower than the rate for N2, right? 52 compared to 79. And that's how we answer that question. All we did was first find the ratio of the rates, which was 0.6613, and then for the rate of N2 here, we substitute the rate of 79 milliliters per second that the question actually gives us. And in the end, we get 52 milliliters per second as a rate of SO2. All right, let's look at number 39. Again, if you haven't done this yet, please pause the video and do so first, and then we'll continue. Okay, so it says it takes 243 seconds for some amount of mole of xenon gas to diffuse, so that's the rate of xenon gas. The rate of Xe is 4.46 by 10 to the minus 5 moles, right, over 243 seconds. That's the rate. The amount is measured in moles, the time is measured in seconds. Okay. Under the same conditions, they want us to find the time for neon gas, but they give us the amount of neon gas. Yeah, it's also 4.46 by 10 to the negative 5 moles. Okay, so let's set up this equation. So since neon gas is the unknown here, I'll keep that on the top in my rate equation. So the rate of neon over the rate of what's the unknown? Xenon. There we go. Is equal to the square root of the molar mass of xenon, which is 131.29, divided by the square root of the molar mass of neon, which is 20.18. This is where periodic table comes in useful. This gives me 2.551. Makes sense. Neon should effuse at a much higher rate than xenon because it's a much lighter gas. Okay, so now that we have the ratios, I'm going to plug in, I'm going to first find the rate for neon. So the rate for neon is equal to, right, 2.551 times the rate for xenon, which is, it's right over here. It's 4.46 by 10 to the negative 5 moles over 243 seconds. Okay, and then you could do all of this math. I'm not going to do this math because now I'm going to move straight into, and things are going to cancel out nicely. You're going to see I'm going to move straight into actually finding the time for neon, right? So time for neon. Let's look at rate equations like speed, right? Speed is a rate equation. So rate of speed, let's call that, is distance over time. So if we wanted to find for time, right, it's going to be distance over rate. In this case, we're not measuring distance, we're measuring amount of gas per time. So if I change this to just amount, we find that time will be amount over divided by rate. So let's change this equation now to find for time. It will be amount of neon, which is 4.46 by 10 to the minus 5 moles of neon, divided by the rate, which is right here. So it will be divided by 2.551 times 4.46 by 10 to the negative 5 moles. Let's put these in parentheses, times 243 seconds. The denominator here goes to the numerator because we're dividing. So let's see, this will cancel exactly with this number. That's why I didn't find the answer there. And so we're left with 243 seconds divided by 2.557 or 2.551, sorry. And that all comes down to 95.3 seconds. And that is the time it takes for neon to diffuse through the same opening under the same conditions. So what did we do? We had the rate for xenon, we had the amount of neon. We needed to find the time for neon. We find the ratio of the rates. We find that neon should occur at a rate of 2.551 times faster than xenon. And so the rate for neon will be 2.551 times the rate for xenon, which is moles over seconds. However, to find the time, we needed to use the amount, which is the moles of neon, divided by the rate that we just calculated in the previous line, and that gives us 95.3 seconds. Does this answer make sense? Yes, it does. Neon is a much lighter gas than xenon, and so for the same amount of gas to escape, it will take a shorter amount of time, 95.3 seconds compared to 243 seconds. Okay, let's look at number 40. Again, please try it first, and then we'll go over it together. Okay, in number 40, we have some balloon that's filled with helium, and it deflates to 2/3 of its volume in 8 hours, right? Now they're asking how long will it take an identical balloon filled with same amount of moles of air? They give us the molar mass of air, which is close to the molar mass of nitrogen, to deflate to half of its original volume. So let's look at the rate for helium. It's 2/3 of the volume, that's the amount. So 2/3 is 0.666 repeating, let's call it 667 amount of the balloon. So BALOON, so that per 8.0 hours. That's our rate. Rate of helium, it's 0.667 of the balloon in 8 hours. Okay, so they want us to find the time for air, but they give us the amount of air that we need to focus on, and it's half of the balloon, so it's 0.5 of the balloon. Whoops, 2 O's. Okay, so we have the rate of helium, the time for air is what we need to find. We know the amount of air that we need to work with. So let's solve this. So the rate of air over the rate of helium should be the square root of the molar mass of helium, which is 4.00, divided by the square root of the molar mass of air. They give us 28.2 grams per mole. So this all comes out to, let's see, 0.377, which makes sense. Air is heavier than helium, so the rate of effusion will be lower than the rate of effusion for helium. Okay. So now that we know that, let's solve for the rate of air. So the rate for air, right, will be 0.377 times the rate for helium, which is 0.667 of the balloon over 8.0 hours. That's how long it takes. But we don't want the rate for air. I mean, we could solve this. I mean, we'd find a rate for air. But what we want, well, actually, if you punch this in your calculator, you get a number like, let's see, 0.0314 of the balloon every hour, right? So I did solve for a rate of air. So now the time for the diffusion of air would be, remember, time is amount over, hang on, let's do it again. Rate is amount over time. So that means that time should be amount over rate. I forgot that for a second. So time for air should be the amount of air, which we said was 0.5 of the balloon, that's half of the balloon, over the rate for air, which is 0.0314 of the balloon time per hour. So hour goes on top now. So balloons will cancel out, and so we're left with, if we do this calculation, I believe we're left with 16 hours to 2 sig figs. Does this make sense? Well, helium deflates to 2/3 of its volume in 8 hours. Air, it has a higher molar mass, so it'll effuse at a slower rate, which means that it will take a longer time to go down to a similar or close enough volume. Okay, I'm hoping all of this makes sense. We're just manipulating essentially these equations. That rate is just amount of something over time, and also the rate of effusion of gases, this ratio here. Those are the only equations that we're using, just in different ways to solve different problems. All right, let's try number 41. Same equations, we're just trying to solve for a different quantity. All right, so the rate of some unknown gas is 1.66 times more rapidly than CO2. What is the molar mass of the unknown gas? So the rate of the unknown over the rate of CO2 is 1.66, right? The rate of the unknown is 1.66 times more rapid than CO2. So that's what the equation says. But we know that this is equal to the square root of the molar mass of CO2. I'll write it like that, divided by the molar mass of the unknown. But we know the molar mass of CO2, right? We've calculated lots of times, but if you didn't remember what it was, the molar mass of CO2 is 44.02 grams per mole. So if we wanted to find the rate, if we wanted to find the molar mass of the unknown, let's multiply both sides by this. So we have the square root of the molar mass of the unknown, and that should be equal to the square root of 44.02 grams per mole divided by this 1.66. I've just sort of cross-multiplied, if you will. So if I wanted to find the molar mass of the unknown, I just need to square both sides, right, to get rid of the square root right here. And so that will be equal to 44.02 grams per mole divided by 1.66 squared. And so this all comes out to be, if I did my math correctly, 16.0 grams per mole. Now the next part of the question is, can you guess the identity of the gas? Well, what gas has a molar mass of about 16 grams per mole? I'm not sure what I was thinking when I set this question up, but methane, right? CH3 gas has about a molar mass of about 16 grams per mole. Carbon is around 12. Hydrogen is around 3. Well, that's actually close to 15. Yeah, I'm not sure what gas I was thinking of when I said this question. Maybe I was thinking of oxygen, but oxygen is O2, which has a molar mass of around 32 grams per mole. Okay, let's look at number 42. Hydrogen gas, if used through a porous container, 8.97 times faster than some unknown gas. What is the molar mass of that unknown gas? Try it on your own first, and then we'll go over it together. Okay, so the rate of the unknown, well, the rate of hydrogen over the rate of the unknown is 8.97, right? Hydrogen is 8.97 times faster, and so we know this will be equal to the molar mass of the unknown divided by the molar mass of hydrogen, which is 2.02 grams per mole. So the molar mass of the unknown, square root of the molar mass of the unknown, is equal to 8.97 times the square root of the molar mass of hydrogen gas. All right, to find the molar mass of the unknown, we square both sides, right? So this will give us 8.97 squared times, and this square root disappears, 2.02 grams per mole. And so that all comes out to be 163 grams per mole. I think this is another question where I just randomly sort of made up the numbers, so I'm not sure what gas this refers to. But you can try to figure it out and see if you can make a reasonable guess. But there we have it. Using the rate of effusions from Graham's law, we can figure out the ratios of their molar masses. If we know the molar mass of one gas, we can find the molar mass of the other gas. All right, if you have any questions, please let me know. But in our next video, we're going to look at the kinetic model molecular theory. We'll see you then.